In this video, we look at three different ways of writing chemical equations for reactions in aqueous solutions, namely by using full molecular equations, full ionic equations, and net ionic equations. We'll start with a very brief description of each before going into more depth, starting with full molecular equations. Here is an example of a full molecular equation where aqueous solutions of calcium hydroxide and sodium carbonate are mixed together to form a solid calcium carbonate precipitate and aqueous sodium hydroxide. All of the compounds represented in this chemical equation are ionic compounds, and three of them are strong electrolytes, meaning they are highly soluble in water and also meaning that they exist predominantly as separate ions in solution rather than as intact whole compounds. A full molecular equation such as the one shown here is a chemical equation where each of the substances are written as if they were molecular compounds even when we know they are not. In full ionic equations, ionic substances that are strong electrolytes dissolved in water are written out as separate ions in solution. And here is an example of a full ionic equation where we see that the soluble calcium hydroxide compound is written as separate calcium ions and separate hydroxide ions. And the soluble sodium carbonate compound is written as separate sodium ions and separate carbonate ions. And the soluble sodium hydroxide compound is written as separate sodium ions and separate hydroxide ions. You will also note that the solid calcium carbonate that is formed is insoluble in water and therefore not a strong electrolyte and therefore not written as separate ions but rather kept intact as the whole ionic compound. Net ionic equations represent the overall net chemical change that occurs, and they do not include substances that effectively play no direct role in chemical change. And we will see in a moment that the net ionic equation is simply the full ionic equation with the spectator ions cancelled out. And we'll also see what that means in just a moment. So let's look at each type of equation in a bit more detail, starting with full molecular equations. In full molecular equations, substances are written as if they were molecular in nature, even if they are not. Full molecular equations are very useful as they allow us to physically imagine or picture exactly what is going on with each reactant and each product in solution. For example, when this equation is written as a full molecular equation, we can easily imagine that this solution here is being mixed with or reacted with this solution here to produce these products over here. One of which is a solid precipitate that settles to the bottom of the container, and the other is a soluble salt in aqueous or dissolved form in solution. In reality, however, if we were to look more closely at the calcium hydroxide solution on the left and looked at the atomic scale, we would see the solution is actually comprised of dissolved calcium ions and dissolved hydroxide ions in a 1:2 ratio as per its chemical formula. And if we were to look more closely at the sodium carbonate solution, we would see dissolved sodium ions and dissolved carbonate ions in a 2:1 ratio as per its chemical formula. And lastly, if we were to look more closely at the sodium hydroxide solution sitting above the solid calcium carbonate, we would see dissolved sodium ions and dissolved hydroxide ions in a 1:1 ratio as per its chemical equation. So to go from the full molecular equation shown here to the full ionic equation shown here, we identify all the strong electrolytes dissolved in solution and write them as their separated ions in solution. So the calcium hydroxide solution is represented as a separate calcium 2+ ion and 2 hydroxide ions as per the chemical formula for calcium hydroxide. Similarly, the sodium carbonate solution is represented as separate ions with 2 sodium plus ions and 1 carbonate CO3 2- ion, as per the chemical formula for sodium carbonate. Now, if we look at calcium carbonate, we note that calcium carbonate is a solid. It is not soluble in water. It is not a strong electrolyte. It does not exist as separate ions in solution. And so just keep its chemical formula as it is, as CaCO3 with the S subscript representing a solid. And finally, sodium hydroxide, NaOH, is soluble in water. It is a strong electrolyte, and so we represent it as separate sodium ions and separate OH- ions dissolved in solution. And we also show that there are 2 of each of these ions corresponding to the stoichiometric coefficient of 2 in front of the NaOH in the full molecular equation. To get to the net ionic equation, we identify the overall net chemical change that has taken place. To do this, we need to identify the spectator ions in the full ionic equation, those ions that do effectively nothing in terms of any chemical change that occurs. And we need to cancel them out on each side of the chemical equation. And we identify the spectator ions as those ions that undergo no physical or chemical change in going from one side of the chemical equation to the other. So if we go back to the full ionic equation, we can see, for example, that the two hydroxide ions on the left-hand side of the equation undergo no physical or chemical change and appear as dissolved ions in solution on both sides of the equation. We can therefore cancel these ions out on each side of the equation. We can also see that the two sodium ions undergo no physical or chemical change and appear as dissolved ions in solution on both sides of the equation. And so those ions can be cancelled out. In this particular example, the hydroxide ions and the sodium ions are said to be spectator ions. They take no part in the overall net chemical change that occurs. The remaining ions in solution, the calcium Ca2+ ion and the carbonate ion, do in fact undergo change as they end up as the solid calcium carbonate precipitate. And it is these three chemical species that remain left over in the net ionic equation. So just to reiterate, the net ionic equation is the full ionic equation with the spectator ions cancelled out. In conclusion, and to summarise, for the full molecular equation, we write out all chemical substances in full. We then balance the equation and we write all appropriate subscripts for each substance, like this. For the full ionic equation, we write out all strong electrolytes as separate dissolved ions in solution to get this. And finally, for the net ionic equation, we identify and cancel out all spectator ions to get this as the overall net chemical change that occurs for this particular precipitation reaction.